In this video, we are going to discuss about the electrode potential and chemical reactivity of transition elements. Electrode potential and chemical reactivity. In solution, the stability of a compound depends upon the electrode potential value. And the electrode potential value depends on three factors. That is, E0 value depends on three factors. They are the enthalpy of atomization, ionization enthalpy, and hydration enthalpy. So based on the value of enthalpy of atomization or enthalpy of sublimation, ionization enthalpy and hydration enthalpy, we decide the value of E0, and depending on the value of E0, we decide the stability of the transition metal compound. Now, something you have to note here, that is low E0 value. Low E0 value means it will be negative E0 value, electrode potential value. Then high oxidation state is stable, and high E0 value. High E0 value means positive E0 value. In that case, low oxidation state is stable. So keep this in mind. That is, low E0 value, high oxidation state is stable, and high E0 value, low oxidation state is stable. Also, we have discussed in chapter electrochemistry that negative E0 value means that it can act as a reducing agent, means they want to get oxidized, and positive E0 value shows that it can act as an oxidizing agent, that is, they want to get reduced. So let's keep all these things in mind and let's see the electrode potential value, how it varies for transition metal compounds or transition metals. So here I have written for the first transition series, the E0 values are written, that is E0 M2 plus M, that is the reduction potential for the reduction of M2 plus ion into metal atom is written here, and you can see the E0 values, vanadium to zinc is written on the board for the reduction of M2 plus to metal. Now let us discuss few questions based on this first transition series, E0 M2 plus M of the first transition series. Now the first question is, you can see that there is a irregularity in the above values, means there is not increasing or decreasing in a particular order. Now what is the reason for the irregularity in the values of E0 M2 plus M for the first transition series? And the answer is due to irregular variation of the ionization enthalpy. So this irregularity in the values is due to irregular variations. Irregular variations of ionization enthalpy. Now ionization enthalpy means we have to consider the sum of first and second ionization enthalpies. So the answer is this. Now the next question is the E0 M2 plus M values of zinc and manganese is more negative. You can see the value of zinc and manganese. Manganese E0 value is minus 1.18 volt and zinc is minus 0.76 volt. Now why is these values more negative? First let's take for zinc. Now E0 Zn2 plus slash Zn is minus 0.76 volt, means it's a low value, low E0 value, means it is negative. So I told you, if the E0 value is low, then high oxidation state is stable. So which is the oxidation state highest here? Zn2 plus. So Zn2 plus is stable. Let's write the electronic configuration of Zn2 plus. So Zn2 plus electronic configuration is argon 3d10. So you write the electronic configuration of Zn2 plus, and why is the E0 value negative for zinc? Due to stable 3D10 configuration. Now the next question is E0 value, E0 M2 plus M for manganese is negative. Now for manganese, let's write the electronic configuration of Mn2 plus. Electronic configuration of Mn2 plus is argon 3d5. So the E0 value is negative due to stable half-filled D5 configuration, and also there is one more reason, due to very low sublimation enthalpy value for manganese. So there are two reasons for the negative E0 M2 plus M value for manganese. The first reason is due to stable half-filled D5 configuration, and second is due to low sublimation enthalpy value for manganese. Now the next question is E0 Ni2 plus Ni is negative. Now if you look, you can see that E0 value of nickel is minus 0.25. Now why that E0 value for nickel is negative? Answer is due to high negative hydration enthalpy of nickel. That is the answer. So since the hydration enthalpy is more negative, the E0 value becomes negative for nickel. Now the next question is E0 vanadium 2 plus vanadium is low. Low means, if you look here, you can see that vanadium is minus 1.18 volt. So why that E0 value of vanadium 2 plus slash vanadium is low, that is minus 1.18 volt. Now the answer is, when you write vanadium 2 plus, what is the configuration? Vanadium 2 plus is argon, then vanadium is 3d3 Now vanadium 2 plus means 3d3, so argon 3d3. Now vanadium 2 plus is stable with half-filled T2G3 configuration. So it has a very low E0 value. Okay, so the answer here is due to stable half-filled T2G3 configuration of vanadium 2 plus. The E0 value of vanadium is low. Now the next question is the E0 value of Cu2 plus Cu is positive or plus 0.34 volt. Now what is the answer for that? That E0 value depends on the sum of enthalpy changes. Which are the three enthalpies involved or that decide the E0 value? Enthalpy of atomization, ionization enthalpy, and the hydration enthalpy. So you can see that copper has, this copper, it has high enthalpy of atomization, and we know this enthalpy of atomization means it is the energy absorbed. And copper has low hydration enthalpy. Hydration enthalpy is the energy released. So it has high enthalpy of atomization and low hydration enthalpy. Now the high energy required to convert or transform copper to Cu2 plus is not balanced by its hydration enthalpy. So E0 Cu2 plus Cu is positive. That is, you can see that copper, the electronic configuration of copper is argon 3d10 4s1. Now Cu plus means argon 3d10. Now the second ionization enthalpy will be very high for Cu plus, because the second electron has to be removed from stable 3d10 configuration. So you can see the ionization enthalpy is also the energy absorbed. So in this case, atomization, enthalpy of atomization and ionization enthalpy both are positive, and the hydration enthalpy, which is negative, that is very low, which means the positive charge is more. So, the E naught value of copper is positive, or you can say that the high energy required for the transformation of copper to Cu2 plus ion is not balanced by its hydration enthalpy. So, the E naught Cu2 plus Cu is positive. Now, the next question is, so that is the only element, copper is the only element whose E naught value is positive in the first transition series. Now, the next question is, copper 1 Cu1 is not known in aqueous solution. Copper 1 is not known in aqueous solution, or you can say Cu plus ion is not stable in aqueous solution, or you can say Cu2Cl2 or CuCl2, which is more stable in aqueous solution, and why? So, three questions we have same answer, that is copper 1 is not known in aqueous solution. Copper 1 means Cu plus, or Cu plus ion is not stable in aqueous solution, or out of Cu2Cl2 or CuCl2, which is more stable. Cu2Cl2 means here we have copper in plus 1, CuCl2 means we have copper in plus 2 oxidation state, and we know copper 1 is not known in aqueous solution, means this does not exist, CuCl2 will exist, means CuCl2 is stable in aqueous solution. Now, let us see the answer for this. Now, Cu2 plus, so we can say Cu2 plus is more stable in aqueous solution than Cu plus in aqueous solution. This is because the second ionization enthalpy of copper is large. I told you the second electron in copper has to be removed from stable 3d10 configuration. So, the second ionization enthalpy is very large, but the hydration enthalpy for Cu2 plus is more negative than Cu plus in aqueous solution. So, what happens? It more than compensates for the second ionization enthalpy of copper. Okay, so although the second ionization enthalpy is higher, but the hydration enthalpy for Cu2 plus is much more negative than Cu plus, and hence that more negative hydration enthalpy compensates for the second ionization enthalpy of copper. Therefore, Cu1 or Cu plus in aqueous solution will undergo disproportionation, and it undergoes disproportionation to form Cu plus Cu plus undergoes disproportionation to form Cu2 plus Cu. Here one Cu plus will get oxidized and one Cu plus will get reduced. This is reduction. Okay, so always in aqueous solution which is more stable, Cu2 plus is more stable, not Cu plus. Now the next question is, copper cannot liberate hydrogen from acids. Why? We know that the E naught value of copper is positive, that is plus 0.34 volt. So, it is a weak reducing agent. Plus value shows that it is a good oxidizing agent but a weak reducing agent. So, this copper is a weak reducing agent than hydrogen. So, this copper cannot reduce H plus of acid to hydrogen gas. So, copper cannot liberate hydrogen from acids, but copper reacts with oxidizing acids like HNO3, H2SO4, etc., and it can release hydrogen gas. So, this is about the E naught M2 plus M of the elements of first transition series. Now, next I have written here, for the first transition series, the E naught M3 plus M2 plus, that is reduction of metal in 3 plus to 2 plus state. The E naught values are written on the board from titanium to cobalt. Now again let us discuss few questions based on this E naught value. Now look at this series, and the first question is identify the two strongest oxidizing agent in aqueous solution. Now, strongest oxidizing agent means the one with more positive E0 value. So, who are the two with positive E0 value? One is manganese, that is Mn3 plus, and the other is cobalt. So, which are the two oxidizing agents here out in this series? Mn3 plus and CO3 plus, as both have more positive E0 value. Now, the second question is E0 M3 plus M2 plus of scandium is very low. Scandium, I have not written the value, but if you look in the books, you can see that the E0 value of scandium is very low. Now, very low means the high oxidation state. E0 value low means which oxidation state is stable? High oxidation state is stable. That is, scandium 3 plus is stable than scandium 2 plus. We know that scandium 3 plus is stable with what? The noble gas configuration. So, the E0 value is very low. Now, the next question is E0 M3 plus M2 plus of zinc is high. Now, zinc is high means high E0 value. High E0 value means the low oxidation state is stable. So, we can say Zn2 plus is stable with stable D10 configuration. So, Zn2 plus is more stable than Zn3 plus. Now, the next question is E0 Fe3 plus Fe2 plus is low. Why the E0 value of Fe3 plus Fe2 plus is low? E0 value low means the high oxidation state is stable. So, we can say Fe3 plus is stable than Fe2 plus. Now, why is Fe3 plus stable? Now, ion electronic configuration is argon 3D 6,4s2. Now, Fe3 plus means the configuration is argon 3D5. So, Fe3 plus is stable due to half-filled D5 configuration. Now, the next question is E0 Mn3 plus Mn2 plus is more positive. Now, more positive means E0 value, high E0 value means low oxidation state is stable, means Mn2 plus is stable, and we know Mn2 plus is stable with half-filled D configuration. Now, next question is E0 Cr3 plus Cr2 plus is minus 0.4 volt. Now, minus means E0 value is low. E0 value low means high oxidation state is stable, means Cr3 plus is stable. Now, chromium electronic configuration is argon 3D5 4s1. Now, chromium 3 plus means the configuration will be argon 3D3. So, this chromium 3 plus is more stable due to half-filled T2G3 configuration. This explanation for chromium, stability of chromium 3 plus is based on CFT. So, due to T2G3 configuration. Okay. Now, the next question is chromium 2 plus can liberate hydrogen from dilute acid. Why? Chromium 2 plus can liberate hydrogen from dilute acid. Chromium 2 plus liberate hydrogen. Now, you know that the E0 Cr3 plus Cr2 plus is negative. Negative means that Cr2 plus is a strong reducing agent. So, reducing agent can help in the reduction of H plus to hydrogen gas. So, the equation will be 2Cr2 plus plus 2H plus gives 2Cr3 plus plus hydrogen gas. So, Cr2 plus can liberate hydrogen gas. Now, the next question is, which is a stronger reducing agent, Cr2 plus or Fe2 plus and why? This is a very important question. Which is a stronger reducing agent? Stronger reducing agent. That is Cr2 plus or Fe2 plus. So let's write the electronic configuration of chromium. Chromium is argon 3d5 4s1 and iron is argon 3d6 4s2. Now let's write the configuration of chromium 2 plus. It is argon 3d, 2 plus means 3d4, and iron 2 plus will be argon 3d6. Now we know that we have to find out who is the better reducing agent, chromium 2 plus or Fe2 plus. Now we know that reducing agent will undergo oxidation. So Cr2 plus undergo oxidation by losing one electron and Cr2 plus changes to Cr3 plus. So what will be the configuration of Cr3 plus? Cr3 plus will be argon 3d3, and you know Cr3 plus is stable with half filled T2G3 configuration. Now Fe2 plus is a reducing agent, means it undergoes oxidation by losing one electron. Fe2 plus gets oxidized to Fe3 plus. So what's the configuration of Fe3 plus? Fe3 plus will be argon 3d5. Now Fe3 plus is also stable with half filled D5 configuration. So based on this we can say both are stable. Okay, and both are good reducing agents. Now let us compare the E0 value and find out which is a better reducing agent or which is a good reducing agent. Based on the electronic configuration we found that both are good reducing agents because both will get oxidized to stable oxidation state, Cr2 plus as well as Fe2 plus. Now let us try to predict the strength of that reducing agent, whether Cr2 plus or Fe2 plus, on the basis of E0 value. Now E0 value shows that Cr3 plus is more stable than Cr2 plus. Let's see write the E0 value. E0 value for Cr3 plus Cr2 plus is minus 0.41 volt. This is a negative value, and E0 value for Fe3 plus Fe2 plus is plus 0.77 volt. This is a positive value. Now E0 value negative means that this is a very good reducing agent. Cr2 plus is a very good reducing agent, or we can say Cr3 plus is more stable. Low E0 value means high oxidation state is stable. So since this is negative, Cr3 plus is more stable than Cr2 plus, and so Cr2 plus can be easily oxidized to Cr3 plus. So it's a good reducing agent. But E0 value for iron is positive, which means that higher E0 value, low oxidation state is stable. That is Fe2 plus is stable based on E0 value. So Fe2 plus is stable than Fe3 plus. So Fe2 plus is not easily oxidized to Fe3 plus. Therefore we can say which is a better reducing agent. Cr2 plus is strong reducing agent than Fe2 plus. Okay, so this is a very important question. Now we have another question, and the question is, why are Mn2 plus compounds more stable than Fe2 plus towards oxidation to +3 oxidation state? That means Mn2 plus is stable towards +3 oxidation state, means Mn2 plus does not want to go to +3, whereas Fe2 plus wants to go to +3 oxidation state. So let's try the electronic configuration of manganese. Manganese is argon 3d5 4s2. Now let's write for Mn2 plus, it is argon 3d5. Now why is Mn2 plus stable? Due to half filled extra stable configuration. So it is very difficult to remove the third electron from this 3d orbital. So delta H 3I will be very high for Mn2+ or manganese. Now let's see for iron. Iron configuration is argon 3d 6 4s2. Fe2+ will be argon 3d6. Now you know that the delta H3I, delta H3I means the energy required to remove the third electron will be less for iron, because on removing the third electron iron will get 3d5 stable configuration. So delta H3I of iron is less. Okay, so these Mn2+ compounds are more stable than Fe2+ towards +3 oxidation state. Now we have a last question, that is for M2+ M and M3+ M2+, the E0 values for some metals are as follows. So I have written here for M2+ M on left side and M3+ M2+ on right side. Now there are two questions based on this. The first question is, the values are written for chromium, manganese and iron. First question is the stability of Fe3+ in acid solution as compared to that of chromium 3+ or Mn3+. So we have to check the E0 value of this. That is, we have to comment on the stability of Fe3+, whether it is more stable, less stable, or is the stability in between the chromium and manganese. So we know that the values are negative and two positive values, and positive value shows that they are good oxidizing agent and they get reduced easily. So large positive value means easy reduction. So on the basis of that, if you arrange, we know that E0 Cr3+ less than E0 Fe3+ less than E0 Mn3+. This order is on the basis of reduction potential values. I have arranged these ions in the order of their reduction potential value. In the increasing order I have arranged. Okay. Now tendency for reduction will be also in the same order. For reduction will be in the same order. That means Mn3+ has a greater tendency to get reduced. This I have written in increasing order. So what will be the stability? Mn3+ wants to get reduced. So it is less stable. So what will be the order of stability of M3+ ions? The order of stability of M3+ will be Cr3+ greater than Fe3+ greater than Mn3+. Okay, because Mn3+ wants to get reduced to Mn2+ easily. So the stability will be more for chromium 3+ than Fe3+ and Mn3+. Now the next question based on this is the ease with which iron can be oxidized as compared to a similar process for either chromium or manganese metal. So there is a second question, the ease with which iron can be oxidized as compared to a similar process for either chromium or manganese metal. For that we have to consider these E0 value. This E0 value we have to consider. So we know that more negative E0 means they will oxidize easily, means they are good reducing agents. So the ease of oxidation, that is the question. The ease of oxidation will be in the order manganese greater than chromium greater than iron. So this will be the ease of oxidation. Means you know that more negative means good reducing agents, they are easily oxidized. So here manganese has more negative value greater than chromium greater than iron. So with this we complete the electrode potential and chemical reactivity of D block elements. Thank you.